All right, I'll get started. Yeah, so happy to present to you today some more stuff on Azure Orbital. We had a brief talk about that yesterday, and then hand it over to Craig to go really in deep on RF sim in Azure and how we do spectrum processing. So Azure Orbital is our new managed service for space and constellation operators. And the whole working idea is we take the cost of the ground stations and kind of offset that for you by putting them at data centers and other teleports. And the going in philosophy for Orbital is to be very closely tied in with the industry and partners. So we are very much partner focused, and like we work hand in hand with a bunch of people to stitch together different solutions. And there's two scenarios. We have one for global comms, which is for like mega internet constellation providers, and there's one for Earth observation, which is kind of like more applicable here and for those kind of LEO constellations that want to do a lot of stuff in Earth observation. So some of the key stats is we had our launch last year at Ignite 2020 in September, and we're going to, right now we're in private preview, which means we have a few customers. It's a little bit more guarded access. It's kind of like a special guarded beta access, and we'll go to public preview in December, which means more people. It'll be generally open to the public, and a lot of you guys will be able to get on and try it. We have our Washington and Sweden sites up, and we'll have the next 4 you can see on the screen there end of next year. Like I mentioned, we're very much partner focused, so we have a deep integration with other partner networks like KSAT and Viasat. And the working idea is you can go in through Microsoft to schedule on our sites and their sites, and it's a bi-directional relationship where they can schedule on our sites as well. And I think yesterday I mentioned that we have a huge virtual RF focus. Our dishes are 6.1 meters in size, X-over tracking, so we don't have a keyhole problem if you're familiar with how LEO tracking goes. And those are the bands that we have right there at the bottom, UHF, S, and X band. And those bands are particularly chosen to be the EO bands. So if you look at the ITU tables, those are primarily what spacecraft operators who do like Earth imaging or like radar observations use. And our hope is actually that, with UHF and S band, when we go to public preview here, that a lot of people would be able to take some of what Craig's talking about, the GNU Radio work, and stitch it together with our UHF solutions, because we know there's a lot of CubeSat operators and university operators that leverage GNU Radio. So I kind of talked about this yesterday as well, but I'll go into it again today in more detail. As mentioned, we have a huge investment into virtual RF. So we have those digitizers at the ground sites instead of hardware modems, and we do full digitization of UHF, S, and X band, and that's all the way up to 500 megahertz. And in this screen, the items in dark blue is what like Microsoft or Orbital provides, and the items in the lighter blue on the right side is like what you can put in your resource to kind of stitch together solutions. And there's 2 ways you could do the virtual RF demodulation or modulation for Uplink. You could ask us to take care of it. So we have the managed modem, where we take care of deploying the modem in the chain and load up the appropriate configs for that. Or we can deliver the VITA RF or VITA49 RF right into your virtual network, and you can bring your own modem, or you could kind of deploy the modems from Kratos and Emergent from the marketplace right into your VNet and like create a whole, whatever like scenario you need to accommodate. You can just kind of pick and choose the parts you need and put that together. So I'm gonna kind of like shift gears into more with lab to flight scenarios for the kind of customers we talk about at Orbital. So my background is in the EO space, where I did work at a small satellite operator who did Earth imaging. So I had noticed there's 2 distinct ways you can do testing for your satellite or your EDU radios in the lab. Previously, you would have to procure maybe the same modems that are used at your deployed sites. And these are kind of expensive, they're long lead, and once you have them in-house, like they're only really good for the exact purpose you procured them for, so they're inflexible and are kind of monolithic in the use case. But the flip side of that is they're really good for verification. So you could get this asset. Maybe it's like a mediocre test asset, but it's really good when you have your final spacecraft built and you want to get it. You want to get that verification that'll work when you actually go to a flight with ground stations across the world. The general shift that we're observing is, there's obviously use of the SDR technology. A lot of people use like digitizers like the USRP. These are definitely more cheap, obviously more readily available. And when you have them, not only can they be used just for testing, you could do way more with it. You could like make your own test ground stations, or you could do, if you wanted to be flexible in testing, S-band or X-band, you can create those test setups if you buy something like a SDR. So yeah, that's the next point. Like many use cases are possible, but the only issue is it's not that great for flight verification. So it's pretty awesome that you have this flexible test asset, but what does it mean when you really want to know if it's going to work in flight? So that's where Orbital kind of comes in here and helps bridge the gap, fully leveraging virtual RF. But since we also do the same, you can kind of use the same test methodology to verify that whatever you've built in the lab can also work in flight. And I'll show you how that works in the next slide. So over here is kind of a high-level diagram of the different types of scenarios. So over at the top, I have an example of a USRP that's used, and then you can get something. The ASE stands for an Azure Stack Edge, which is kind of a hybrid cloud device that you can get on a rental basis for less than $1,000 a month. And using the tools that Craig will talk about, you can do stuff with GNU Radio, build up your modems. You can obviously do recording and replays, and you can do stuff for like channel sim. If you wanted to simulate some Doppler effects or add noise and see how your spacecraft radios perform. So on the left side, I have the spacecraft, which represents the same entity you have in the lab, and the same entity on the right side of the operators. So these exact same entities will carry forward into the flight model, where the sites that you see below the USRP are like the Microsoft sites or the KSAT sites. And on the right side is the Azure cloud environment where Orbital resides. And since it's fully leveraging virtual RF, the exact same scenarios you were building with GNU Radio and doing all your channel sim testing, you can just literally lift and like shift them into Orbital and go like seamlessly from lab to flight. And I think it's really powerful. I actually use this a lot for my own stuff. And one of the neat things with the ASE is it's more than just compute. It can do stuff like synchronize storage with the cloud automatically. So you could do a bunch of back-to-back testing in the lab and then later like use it for additional processing in the cloud. So that's just like one of many ways you could use what we're developing here. And my last slide is another touch on the topic of DIFI, where our goal is to create this open interoperable standard that everyone agrees to conform to. And this is the first standard approved by the board is down there. And so far we have all these companies part of the ecosystem. And I'll hand it off to Craig to talk about exactly how we accommodate RF in the cloud.
Cool. So, like Hrishi said, I'm Craig. I'm going to walk you folks through some of the early work we've done related to applying cloud resources towards doing RF signal processing. So some of the proof of concept work we've been working on, it falls out of some of the experience that people had on our team when we were at previous positions helping out run DARPA's SC2 program, the Spectrum Collaboration Challenge, specifically helping, I guess, run the Coliseum, which was a really interesting and really powerful RF simulation kind of testbed. It let you do some really interesting research on RF machine learning. But it was a physical asset, so it had all the limitations that you would expect from something like that. Like specifically, well, you had a maximum cap size on the number of nodes you could simulate at any one time. Your channel complexities had very specific limitations, and it was time shared with everyone else that was using the system. So I mean, it had some caveats. So we wanted to show what could you do if you actually applied cloud scale processing towards this sort of problem. So we went through and kind of looked at all of this. One of the other main issues with Coliseum is it also has a very specific workflow. in that your data is generated on a very specific time scale, and if that doesn't really fit with, like, say, doing very tight loop continuous integration, continuous deployment, you're just kind of out of luck because the resource is built, you can't really change it. So our proof of concept work so far shows that it's absolutely possible to build a cloud resource that's fully configurable and could meet the needs of your development workflow. So this is very high level kind of architecture view of the system. So every block here is a pod or container running in a Kubernetes cluster. So you have a number of transmitters going through some channel models, aggregating all that data, and then going to a receiver. We actually took some of the concepts from GNU Radio in terms of defining the topologies on here. So if you actually look at how one of these is deployed, it looks a whole heck of a lot like a Python flow graph. You just say block A, output 1, talks to block B, input 2. Works out very nice. So the workflow with using one of these systems, generally you start by generating the channel models by simulating a physical environment. And then you apply those channel models to some RF signals. And just one note on this, like we show all of this unidirectional. That's just because this diagram looks really scary if you draw all of the arrows for fully bidirectional. So we just left it here, but there's nothing to say that you can't just do bidirectional. So we work with some of the folks at ANSYS to simulate a small chunk of Seattle. Let me go ahead and play the video. We have a mix of static nodes, some nodes on the side of buildings, some nodes moving around kind of on the ground, and then we've got some airborne nodes, some kind of medium flyers, and then some very high flyers in this zoomed out inset. So we went through, simulated like the physics, actually said, okay, there are a few different material types, and came up with channel models that for each, like a full mesh connection between each transmitter and each receiver. So we boiled that down into a bunch of channel models. In this case, it was 100 by 10, so we had about 1,000 channel models of time-varying complex taps. And then stored those off so they could use those in the next stage. So for the next stage, we wanted to come up with a fairly intuitive way to relate, like what is this effect of the channel? Like how do you relate, I guess, the quality of a channel to someone who's not really a software-defined radio or DSP expert? So we came up with the idea of running an NTSC analog TV signal through one of our channels. You can see up here, we show you kind of the bird's eye view of the topology. We've got a transmitter on the side of the building, and if you can see, we've got a little car down here. Will have the receiver in it, and this car is going to drive down an urban canyon, and then it's going to turn this corner, so you're going to get some nice shadowing effects from those buildings. Over here, you can see kind of the first-person view from the car, just to see where it is along its route. This quadrant down here will show you what the original TV signal would have looked like. And this final quadrant is what the car is actually going to see, the receiver in the car. So I'm going to go ahead and run this. And the neat thing about NTSC is, since it's an analog spec, you get all these fun little effects of, like, when you have low signal quality, you get like the static in the background, or if you have multipath bounces, you'll see some ghosting effects. Like a good one's going to come up soon. Like you can see right along the side, you get some really nice ghosting. And then when you go around a corner and get into a shadow, you just see the signal completely just drop out. So you get a little bit more than that, like digital cliff type effect with some of the more modern TV comm signals. So yeah, this definitely shows that this is a thing that it's totally feasible. But this isn't the product that we're going to try and release right now. We built a bunch of IP along the way that we thought actually might be useful to this community in general. So we're going to walk through some of those pieces and tools. Before I get there, though, I'm sure a lot of folks are asking, well, why would I do SDR in the cloud? What's the point? One good use case is just for access. You can work with your data from literally anywhere. All of your data is available, all of your processing infrastructure. You can be working from a beach, whatever, doesn't matter. It's all available to you, just access remotely, as long as you've got, well, a good network connection. Once you're in the cloud, you can also easily leverage other resources, such as some of our other services, like the Azure Cognitive Services. You can very tightly integrate with cloud-based CI/CD pipelines, or you can talk to services that directly inject RF in the cloud, like Hrishi's working on. Another good use case for moving processing to the cloud is for reliability. Specifically, if you're talking about like storing your data and you want it to be redundant in case of a disaster, You can turn on geo-replication, which makes sure that there's a copy of data stored in a completely different data center, often on a different continent. So you're generally going to be okay in terms of redundancy. And then the last thing to just cover on that is scalability. Basically, can I scale up the use of resources as I need them? And this can be in terms of compute. Like for us, we had this very large scale signal processing problem, but it could be as simple as saying, well, I saw that really interesting talk on RF machine learning. I would like to try and do some GPU accelerated machine learning, but the GPU market's a little bit rough these days. I don't want to go out and buy that physical asset. Instead, you can go ahead and grab some time on one of our GPU enabled VMs and just kind of run it. And then when you're done using it, you turn it back off. And we're also starting to turn on some FPGA instances to let you do some accelerated machine learning with those too. And the last bit is in terms of scalable storage. You get access to massive storage in terms of you can use like Azure disks or Azure files, which are basically like direct attached disks to VMs, or Azure files, which act basically like Samba servers. And then there's Azure blobs. I'll go more into detail on those in a little bit. So one issue that people commonly stumble with in terms of doing cloud processing for the first time is dealing with authentication. Now you have all of these distributed resources. It's not just as simple as logging into a single system and using local resources. You need to actually manage that authentication. So that's something that with the next set of tools that I'll go through, we've actually tried to design those with that in mind. So we call this project Azure Software Radio. Basically, we're trying to allow GNU Radio tools to leverage cloud resources in a much more natural way. The first chunk is our GR Azure Software Radio block, our out of tree module. It's really geared towards, again, making it much easier to use cloud resources directly from within a flow graph. You can use this obviously within a VM in the cloud, but we also made it usable so you could do things locally on your laptops. The second chunk is we have an Azure Software Radio Developer Virtual Machine, which is a VM that's published in our Azure Virtual Machine Marketplace. It's currently in private preview. But what it'll allow you to do is basically deploy an instance without having to do any sort of pre-configuration that has things like GNU Radio and other tools installed. But I'll go into that in a little more depth in a bit. So the first couple of blocks I'll go through is the Blob source and sync block. So they're direct interfaces to the Azure Blob storage and GNU Radio. They're really meant to feel like you're using the basic file source and sync blocks. So like a local use case for this would be if you've got, say, your local laptop, maybe you've got a 256 gigabyte hard drive, you probably have about 100 gigs free, and you're trying to do a signal capture. If you're streaming Complex 64 at 10 megahertz, you're gonna burn through your disk in about 20 minutes. Well, 21. If instead you used the Azure sync block, you could just store directly into Azure Blob and store up to 190 terabytes at a time. So previously, if you wanted to clear out your hard drive, you'd say, well, I get my 100 gigabytes, I store it off, I do whatever processing, and then I either have to back it up someplace else or I have to delete it. This just lets you punch it straight into Blob storage and you don't have to worry about it. A cloud kind of use case might be, say you've got a really massive machine learning data set. And you'd like to run it through, say, some of our GPUs for doing GPU accelerated machine learning. If you have many, many terabytes of data, previously you would have to stand up some storage attached to your VM, copy that data down, and then do your analysis. This lets you just stream massive files to or through your analysis pipeline without having to set anything up ahead of time. So I've been talking about blobs a lot, and I didn't really define them ahead of time. So if you're not familiar with them, basically they're binary large object storage that are durable, scalable, and cheap. If you turn on things like geo-replication, you get something like 16 nines of durability. They're scalable in terms of you can write out to 190 terabytes per a single file, and then if you need more, you just change the file name and keep on going. And in terms of being cheap, tiered pricing, it's basically by how frequently you want to access your data. If you need to access it all the time, we're talking maybe 15 cents per gigabyte per month for what we call our hot storage. But say if you've got a data set and as soon as you delete it, you're gonna need it again, you can just go ahead and put it into archive, and that's something more along the lines of just under $1 per terabyte per month. So you can sock away a lot of data for pretty cheap. And in terms of performance, it'll support the Blob service backing all of this. Will support up to 12.5 gigabytes per second, which is 100 gigabit. These blocks won't hit that speed out of the box. We're still going to have to do an optimization step, but we're going to shoot for at least being able to handle all of the network throughput that like your local system or a VM will be able to support. The next block connects back up to our Azure Key Vault service. It's basically like an online password manager. So what it allows you to do is do things like assign an identity to a virtual machine and then say, hey, this virtual machine has access to this Key Vault store, and then pull down things like database credentials. Or if you're doing encrypted communications, you can store up your crypto keys there. So all you end up having to do is put in the name of the key, and it'll spit out the secret, and it never ends up in your Git repo or in your flowgraph, which is handy since now all of this stuff is using cloud resources. If someone else were to pull your Git repo and get your authentication credentials, now they can start tinkering with your data and costing you money, which we don't want that. The last set of blocks I'll talk about go back to some of the stuff that Hrishi was talking about in terms of the DIFI spec. So we went ahead and ensured that that DIFI spec was open sourced. It's now an IEEE spec. I've got the link to it right here. It is based on Vita 49.2, but now you can go ahead, if you give them your contact information, you can go ahead and just like download the spec for free. So you have access to the spec. We're also providing implementations in terms of a source and sync block. So now you have code that implements that spec where you can talk directly to our antennas in Azure Orbital and other instruments from the various people in the consortium and pull IQ directly from those things right into GNU Radio. So yeah, we're excited for that. So the last tool we'll go into is what we're calling our developer VM. So this is a virtual machine image currently in private preview, but it's intended to enable users to rapidly deploy identical development environments that already have a lot of tools pre-configured and pre-installed for you. So right now we have GNU Radio on there, working instance of Phosphor, XRDP, or VNC, so you can connect to it with just RDP or VNC, whatever you choose, and the NVIDIA grid drivers to let you do remote visualization. And it's all pre-configured. It works out of the box as long as you choose a VM that has a GPU attached to it, at least if you want to get the GPU acceleration. Yeah, so you'll be able to deploy a fully functional development environment with a few clicks. Not that there isn't a lot of great work done on installing GNU Radio, but if you're a new user, it can be a little daunting. So if you want to get people spun up really quickly, we think this is a really interesting way to do it. So if you're interested in tinkering with this before it becomes public, please take a look here. We've got documentation there, and we've got a form to sign up for early access. So we'd love to hear what you guys think about it. What works well, what doesn't, what is it missing, what other tools do you want on there? So a thing that we'll be adding as soon as we get our out of tree module through public or open source release is we'll add those things to it as well. So it's all be ready to go. So when can we have this stuff? So the out of tree module blocks, we're going through making sure documentation is good, finalizing all of our unit tests, making sure we're hitting all the important cases, and in parallel going through our open source approval process. So I can't give a definite date, but soon. It's on final approach. The developer VM, that's already in private preview. So if you're interested, again, go to our link, take a look, sign up, and yeah, we'd love to hear what you have to say about it. So the last thing I'll go through goes back to the lab to flight topic that Hrishi was talking about in terms of helping you develop and integrate your satellite with the Azure Orbital service. So for this demo, we're going to show something representative of an Azure Orbital ground station. It'll be sending samples directly into our DIFI source block. We'll apply some physical effects like Doppler shift and path loss, and they'll store those off to a blob sync. So then if you were a user of the service, you could go ahead, download that blob file, and do something like, send it through USRP and play it back into your satellite and make sure that there's no weird endian issues or anything like that. Make sure that your satellite actually can decode the commands that you would send through Azure Orbital. So go ahead and run that. And I sped this way up because like a typical Leo pass would be somewhere on the order of 15 minutes, and the GNU Radio conference didn't give us this long to talk, so we're going a little bit faster. So you can see this kind of whip across as a satellite goes overhead. And then as it starts to get further away, you can see kind of the amplitude go down. And then when it goes over the horizon, you'll see it cut right off. And there it goes. And then just to keep ourselves honest, we'll switch to a different flow graph and play out that blob source block through phosphor. And you can see the same file. And just make sure that we can round trip it through the service without any degradation. So we'll see that pass go again. And over the horizon, and there we go. And then just one last thing before I let you guys go. So all of the videos that we showed on here, at least that last demo video, that was done and recorded on the developer VM. That wasn't a local thing. That was actually recording from a machine in Azure. And all of the stuff that's running in our booth demo, that's running on the developer VM, and we're using all of the blocks that I just walked through. So they're ready to go, and we would love to hear what you guys have to say about them. So we'll be around. If you have any questions now.
I was curious if you've done similar tests with many UEs, like what's the most UEs you've ever tried simulating at one time?
So we did not boil the ocean on the simulation problem. We kind of stopped at proof of concept, and then we said, well, this is definitely doable. All super interesting things to look at. We just haven't gotten there.
Thanks.
All right, do we have any other questions for the Microsoft team?
Thanks, folks.
Actually, there's a couple online.
Okay, cool.
Question for the Microsoft team. 12.5 gigabytes per second streaming to the cloud is pretty cool. You can stream wideband raw IQ and do all your host processing in the cloud. Is that correct? If you experimented with round trip latency, I'm curious if you can emulate protocol stacks.
We've not experimented with round trip latencies. And in terms of streaming the full 100 gigabit, that is subject to like your internet connection and all of that. So like we can't promise that like your ISP at home is going to hit 100 gigabit. That's kind of between you and your ISP.
So then what are the conditions that you were able to get 12.5 gigabyte? All right, cool. Thank you, Craig and Hrishi.